on with the program. Now we have Dr. Victor and Rusu from the Swiss Supranational Computing Center. And so, Victor, the stage is yours. So please come on.
Can you show my slides, please? So welcome, everybody. My name is Victor, and I work at the Swiss Supercomputer Center. Oh yeah, okay, a bit up. Okay. And then I'm going to introduce you a bit what the support applications we have for molecular dynamics on CSCS, the type of service that we provide there a bit, and also talk a bit on benchmarks, what you can achieve with those applications at CSCS. But of course, before we go into the molecular dynamics aspect of the things, let me introduce a bit what is the Swiss Supercomputer Center, right? So it's a department, it's an institution inside ETH Zurich. So it's part of what's called the ETH board, ETH Rat. So it's part of a set of entities that belongs to the Swiss nation vision of computing capabilities and networking, and was introduced in 1991. We have more or less 114, 115 staff from 23 different nations. So I'm particularly Brazilian. I'm not from Switzerland. And what we do is drive or try to design or operate a computer center that can help scientists do science, right? Or let it be by providing computational infrastructure, let it be by doing allowing for data storage or do some data analytics. We are very, very proud of our institution because we do have a very, say, like top of the line institution and computer center where we are the first supercomputer in Europe, right? So we are the fastest supercomputer in Europe so far for 10 years, for 10 times editions of top 500. So I'm part of what's called the user engagement and support team. So my job is to help anyone who's interested on doing any molecular dynamics or any quantum chemistry run on CSCS, help them to the entire process of running there. So, and that is what we call the user lab or user laboratory, where we provide just a huge number of users our computer infrastructure. So if you have an account of CSCS, if you apply to have an account of CSCS and you want to run molecular dynamics, most likely we're gonna interact with each other. So, and what is our flagship supercomputer? What's inside this building? So this is the building that we have for the offices. So that's where we work, and then this is the building that we have the supercomputer. So what is inside that building on the back? It's our flagship supercomputer that's called PITZNIGHT, right? PITZNIGHT is a Cray-based machine, so it's actually hybrid. So it contains the XC40 and XC50. XC means extreme computing version of the Cray, and where the XC50 is composed of these NVIDIA GPUs, right? And the XC40 does not contain GPUs, it's only CPUs. And we have this hybrid system is a bit unbalanced, in the sense that we have 5,704 GPUs and just roughly 1,800 non-GPU systems, right? So because we have the largest part of the machine is GPU, and you can achieve 25 petaflops with this part only. I'm going to talk about molecular dynamics on this part today, okay? I won't be touching anything related to the non-GPU applications. I'm only going to talk about GPU-enabled applications and benchmarks on using those applications. But as you can see, this machine is not a single computer. It's actually a set of computers. Each one of these towers here we call a cabinet. And then we have several cabinets on the line, if I can say. So we have several cabinets on each one of these rows, right? So if you really want to run at highest performance at CSCS, you need to have at least a bit of the understanding how these machines are connected. Because running of molecular dynamics and you say, I want to run with 1,000 nodes, what does it mean? Does it mean that nodes will fall randomly on these rows, or how's it going to happen, right? So let me give you a 5,000 feet view of the network of this machine and how it's going to imply on our benchmarks. So we are, the network is called IRIS network, and it has a topology, right? So you connect these computers in a certain way. That's the connection on how you connect. It's called topology of the network. And we have this concept of what's called electrical group. And what is an electrical group? We call electrical group because all the machines are connected to a switch. So this is a switch, and we compute the compute nodes there. And all these cables that connect them are electrical cables. They are real copper-based cables that you connect one machine to the switch and switch to the machine, right? So we have a high-dense system, so it's just 4 rows. We can do 5,000, or actually almost 8,000 machines, right? How can we do that? The reason for that is because we have these high-dense nodes, have every blade, every compute blade that goes into this cabinet contains 4 nodes. So it's a highly dense and highly packed system. And how we connect these electrical groups have roughly 160 nodes. So you can have, if you run with more than 160 nodes, you're going to fall in a different electrical group. So your simulation will be split into different electrical groups. And what does it imply? It implies that then when you connect one group to another, you're going to have a fiber optic, right? So if you have fiber optic in your house, just like this very thin cable that connects one switch to another switch, and it's high bandwidth connection. Of course, more local, the better. So if you can run your simulations as much as possible within electrical group, you're going to get the best performance. And if you start to fall into multiple electrical groups, then your performance will still be good, but will not be, how can I say, will not be as good as if you are in the same electrical group. Of course, these machines are very well tuned. So we have tuned the machines. So just to give you an idea, we now have 25 petaflops, right? The machine was built with 17,000 petaflops. How can we get 25,000 now? Because we start to tune the parameters of the network in order to get the best performance ever. So what I'm telling you is that if you run a very long simulation, let's say if you want to simulate 2 billion particles on our system, then yes, this network can handle that because we have tuned it, we have played with the network. So we are very confident that this system can handle large simulations, and we have tested it. So talking about what you can run, what we provide already for you, so you don't have to do much of work, it's the support applications, right? So we have a list of support applications that encompasses molecular dynamics and quantum chemistry, and so those, and also other stuff, but this is chemistry related, biological related. So I will talk today about these 4 initial ones, Amber, GROMACS, LUMPS, and NumD, right? So we have this user portal where you can find this list, and in each individual page, you're gonna find information how to run each individual applications. We also provide what we call a job script generator. So if you're not used to running into a supercomputer where you have a workload manager, where you submit your job to a QE system that schedules your run, we provide you with a tool on our user portal that you can make use of and play around. So you may have used these, or not the script generator, but the scripts to submit your applications during the hands-on part, right? So we also, what's really good about this job script generator is that we have tailored to our needs, right? To really run on our system. So we already provide you the flags needed to share the GPU. That's called this Craycood MPS. We also allow you to already run simulations. So we already give you as default to run on the GPU and also on the without using any virtual cores, only the physical cores of the machine, so to get mass performance on some applications. Another thing that we also provide is that, okay, I do not want to use the GROMACS version that you guys have provided me. How can I use a different one? So we also provide different ones that are not installed, of not only, let's say, a application like Gromax, but for other ones, and also applications that are not by default installed on the system. And how can you find this? Well, we do have a GitHub project online that's open, so where you can find recipes on how to install the applications. And you can easily change application version and run and compile the code on Pittsnight. So we do use a tool to install applications. We don't do manual installations. So we have a robot that goes there and installs it. I mean, by robot, we have a computer program that runs the installations and uses this tool called EasyBuild to generate not only the installations, but also the modules that you see. So everything, all the infrastructure, you can find on this portal. So it's a very good place also to understand a bit how we deploy our software. So with all those introductions about the CSCS and what are the tools that we provide, I want to give you now the real benchmarks, right? The real application that we are running. So let's run the applications. But before that, let's just give you a disclaimer. So I'm going to show you data for performance, and your mileage may vary, right? Because they depend on many things, including your input files, right? So I have a set of input files here. I actually have one input file that's repeated across the 4 applications. So I'm already comparing the same system, same conditions across the 4 applications. Of course, the applications do not support exactly the same algorithms. So let's say Gromax, I use P-links, but on LUMPS, I use Shake to run the simulation. So you're going to see a difference there. But so it will vary depending on your input file. That's what I want to say. It may not only vary, it will vary. So please test what I'm going to show you here. So what is the benchmark that I have chosen to show you? It's a benchmark that was developed in UK. It's called Hack Biosim. And this benchmark is open online. You can download it and you can run. I selected one input file from this benchmark, which contains 1.4 million particles. And why did I select 1.4 million particles? It's because it's the average, let's say ballpark size of the people running on Pittsnight. And it's just a standard bio system where you have a membrane and a protein, some ions and water, right? This box is not in vacuum. This box is inside water, right? It seems underwater. And the force field was chosen was charm 22. That's very important because some applications are tuned for a force field, some applications are tuned for another force field. So I selected just a random one. Actually, I took the one from the benchmark, it's charm 22. And this benchmark provides already for Umber, Gromax, LUMPS, and NumD. That's very useful, right? Because it's actually the molecular dynamics package that we support on Pittsnight. So by chance, this is a very good benchmark for us. So what I want to tell you is that I have ran these benchmarks over and over and over and over, playing with some parameters. So of course, I want to do a scalability test, so I changed the number of nodes I'm running. I also changed what's called tasks per core, tasks per node, and CPU per tasks. So this tasks per node defines how many MPI ranks you have inside your compute node. CPU per task defines the open pthreads, will be translated to open pthreads. And this tasks per core defines how many virtual cores you have. So if I do one, I don't have physical cores, I have 2. I have physical, or two virtual ones, right? Sharing the same core, because that's based on an Intel architecture, right? These machines are Xeon based. And of course, by doing multiple MPIs per node, and every machine has only one GPU, we have to share the GPU. So NVIDIA provides this called MPS. And in order to enable MPS on a Cray system, you have to export this variable Cray CUDA MPS. So let's start with Gromax. You can find the recipe or how I compile the code using these on this link. That's the EasyBuild link that we install. And we have a lot of options that I want to suggest. Of course, you can install this software completely different. It's up to you, right? To install if you want to install yourself. Do not use the ones that we have. But our experience has showed that if you do not enable the build of your own FFTW, that's this option here, you will lose around 5% performance. Gromax lately has had some bugs related to CMake. So then it's better if you define what's the architecture that you're going to run. So by command line, not allow it to detect, because it has been some problems. And we also tell you to turn on these cycle subcounters. I will talk about that later. What does it mean? Because it's not so common when you're building GROMACS. People don't, in general, turn these on. So how does translate to command line? Just that, right? You just do module load the CUDA toolkit to get the GPU module, and then you do module load then GPU to get the CMake, and then you do CMake on your GROMACS, and using these options. That's simple, right? Just talking a bit more about this last option, the cycle subcounters. GROMACS is is the only application that I know that allows you to have more information about their internal counters and how they can help, and how they are used to balance the simulation or let the simulations be, I could say, better scaled on the machine. And that's these subcounters. And if you do, by default it's off. If you do not turn them on, you actually won't get them, the description of these subcounters. And what they do, they print the statistics at the end of your output. So they actually print the statistics after the MD loop finishes. So there will be no impact on your simulations per se. And they are used for load balancing. So they are already there. So they are already being computed unless you turn off load balance on GROMACS. But if you turn on, which is the default, then you'll be computed all the time. And so there's no overhead for your simulation per se, to just enable the printing of these. So, and it's very, very, very useful for understanding how to run on GPU, because the current version of GROMACS 2019, it will change slightly in 2020, but in 2019, they do run simulations between CPU and GPU. So they do the non-bonded part of the simulation on the GPU, and the bonded they do on the CPU, right? So if there's any imbalance between the CPU and GPU, then your code can be running not at speed because your CPU is taking forever. The bonded part is taking forever. And how do you know that? By enabling the subcounters, right? So if you enable the subcounters, you're gonna get an output, additional output, that's this end. So GROMACS by default gives you these at the end a list of counters that they already do, but they don't do the subcounters. And the subcounters contain information like how much time they spend doing the bonded forces, right? So the percentage. So you can play around and try to minimize those numbers. The numbers that you're really looking for that should be very, very high are the ones related only to the force of the non-bonded, because that's running on the GPU. Of course, you change on the 2020 version, but that's not released yet. So, and what about the performance that we can get? So this is the scalability plot of GROMACS on PITS using that input file, right, that we talked about. As you can see, GROMACS changes performance with the version, right? If you have an older version, 5.1.4, you get that performance in red. And if you have the newer version, 2018 or slightly newer version, 2018.3, you get a better performance for a lower number of nodes. And we have a very good collaboration with GROMACS. At CSCS, we have a project that we develop. We're modifying GROMACS to be a bit more librarized so that we can use the non-bonded part outside GROMACS. And we have a very good relationship with them, so you can talk to them easily. And I was asking them why this happens, right? So GROMACS is always aimed for raw performance. So they really want to get the fastest they can get on a single node and then scale that to other nodes. So you can see along the years, they have improved substantially their performance on the lower nodes, right? Of course, that has an impact. That means that you won't scale to that amount of nodes anymore because you are now becoming network bound, right? If you are computing very fast, the next bottleneck will be the network or the I/O, but in this case, it's the network, right? So, and one of the nice things about using these benchmark that we're using is because they're completely public, not only the input files, but also the output. So on the output, we can compare what if we are doing good or bad on our system compared to someone else's system, right? So The people from UK have this new machine called Archer, where it's ARM-based, and then we can compare if their output, what they're getting, is similar to what we are getting. So as you can, Archer is a CPU-based machine, okay? It does not have GPU. The GPU is on the JADA machine, And you can see we are doing pretty well, right? We are around 2 times faster on the GPU comparing to the CPU, and this is 24 cores, and we are just running in one CPU here, right, per MPI. So it's 12 MPIs and one CPU. So we are doing pretty well. And to get the same performance, you can go in 16 nodes, more or less, you get the same performance as you would get in 64 on Archer. So we are very, very good with that, so that we can compare, right? So after talking about GROMACS, I'm going to move now to the next application that's called UMBR, right? And UMBR is slightly different than GROMACS because UMBR is meant to be used in small clusters where they have high dense numbers of GPUs. So UMBR is not an application that was, for the GPU part at least, is not meant to run into multiple nodes, but in a node that contains, I don't know, 20 GPUs. So it's a slightly different approach to the simulations than GROMACS, but we suggest you to compile it and run it. If you have the license to do UMBR, but you can do module load on our system. And the way we install it, and we suggest you to install it, is by fixing the patch versions. We had some issues with some professors because they were running UMBR, and then we upgraded UMBR, the patch version, and then suddenly the simulation started to give different results. So on the patch version, they fix some bugs and stuff, but they do not show up on the version number. It's still UMBR 18, let's say, when you change the patches. So we provide a module with the name of the version and the patches that we install. But if I were you, I would fix to a patch and run your simulation if you want to get reproducibility, because the next patch can change your results. And so the UMBR is as I told you, does not scale on multiple nodes, and as you can see on this graph, right? So you can get a very good performance in a single node on PITSTINE. It is, until today, October 10th, as far as I know, the fastest code to run in a single GPU implemented, right, to run in a single GPU, but does not scale, it has a negative scalability on more than one node. Of course, as I told you, this will change. This changes if you have multiple GPUs in the same node, but that's not our case. And comparing also what's implemented in Archer, so we have they don't provide any numbers for JADA. So on our case, we have like 6 times more or less, actually more than 6 times faster than Archer if you run on a GPU compared to the MC, because UMBR does not run so fast on the CPU. But as you can see, in one node, you can beat 64 nodes, right, of UMBR MC. So if you have that workflow where you are doing a screening of, let's say, drugs, and you want to do, you select several drugs and you find out those 50 targets are the best drugs for you, you can run UMBR in a single job and one UMBR instance per node at the same time, PITSTINE 50 node jobs, and run everything in parallel. And then you're going to get very good performance. So that's one of the use cases that we have for UMBR on PITSTINE. As you can imagine, as an HPC center, why would you have a code that doesn't scale? The reason is because it's one of the fastest on a single GPU, so you can do this embarrassing parallel type of workflows of molecular dynamics using UMBR very well. The next code is LUMPS. LUMPS is let's say, more interface code than UMBR and GROMACS, because UMBR and GROMACS are more bio-oriented. LUMPS has a lot of different force fields and can do a lot of material science. And the way we install LUMPS is just with GPU. We don't do with Cocos, but that depends on your input files. The input files that we have, GPU gets better, so we didn't provide with Cocos, right? So this is the scalability of LUMPS on our system. And you can see it scales pretty well on our system. So comparing to what happens with Archer, you can see that we are doing more or less 2 times faster running the GPU comparing to the CPU on our system. The next code, so why would you use lumps? In general, people use lumps because they are looking for the features, right? They're looking for embedded Aptom model, or they're looking for a different, they're used to that workflow where they're driven by Python. So the next code is NumD, and NumD is a bit careful because you need to compile this Charm++ compiler, and that compiler requires you to already compile with a network connector. In our case, we suggest you to use the UGNI, which is network connector for Cray. So it's the underlying fabrics that controls the entire network. And if you use MPI, you're gonna have a bit of overhead. So the way we compile it and run it, we also do module load with the Cray huge pages. That's this line here, because it's a task-based framework, so it sends a lot of small messages. So it's really good when they pack a bit of message and they send, rather than being sending very small ones. So these huge pages allow for that better balance of the memory and the network on that case, for at least for this input file. And this is the results we get for NumD, right? And if you can compare with Archer, we also pretty happy with the results we get. So you can see Archer scales on the CPU much better than with pitch times on the GPU, but that's a reality on every single code you have. If you start to have a very fast computation, you really have to pay more attention on the network. And that's not the case because machine in general, supercomputers with GPUs are roughly a new thing, right? They're 5 years old. So the people are not doing that so much. So they're not working so much on getting a so much fast GPU and optimizing it. NumD is working on getting this also correct, as far as we know. So, and when you put everything together, right, for all these benchmarks that I showed you, this is what we get. So currently, for this input file that I'm talking to you, GROMAX gets you the best nanoseconds per day, even though it doesn't scale to the same number of processors as lumps, for instance, but it can get you much faster with less nodes, right? If you're looking for embarrassing parallel workflows, as I told you, use Umber, because it goes in one node, and it goes much faster than everybody else in one node, right? And for instance, you need 16 nodes of NumD to be able to beat one node of Umber, just to give you a feeling. Of course, as I told you, this is input dependent, system dependent, so your mileage will vary. So please test, right? Just to conclude, I want to tell you that HPC systems are complex beasts. They do have these topologies of network, so you pay attention to the one that you're running, and you need to measure the application performance. Use your input files. Don't take these preconceived ideas that application A scales better than application B. May be not true for your input file. So we do provide optimized versions of the software, and if you also have a different software that you want to run there that's not listed there, we also help you on compiling the code and optimizing for your needs. And of course, I hope that you guys have fun running on PitStite and have fun doing molecular dynamics. And if you allow me just to give you an additional slide, I just want to talk about the upcoming events. We also do training. So there will be C++ course coming, and we also have a high-performance computing course for Python, so coming. We also had lately this Arrow hack, where we help developers port their code to the GPU. So that's what we did for a week, helping people porting their code. And with that, I'd like to thank you all, and I'll wait for questions.
So thank you, Victor, for this overview. And guys, I have some technical question about
Thank you for your nice talk. I'm an MD user.
Yeah.
And in our cluster, we started to have GPU, so everyone started to use GPU and leave CPU.
Yeah.
So the queue for GPU is too long, and we have so many CPUs free. So I tried instead of waiting for GPU for a long time, is to use more nodes for NAMD.
Yeah.
And with using 2 nodes, it was working well. Then I started to increase it to 4. Then I get an error saying that the number of SMP threads is greater than the number of physical cores.
Yeah.
So the threads will sleep while idling.
Yeah.
So how to avoid this, and what does it mean? I couldn't get the meaning of the.
So when we run it, I didn't go to details, but when we run it, we have to define what's called idle pool here, Pi's idle pool, and this PP number. So these, I would suggest you to always put the idle pool, which means that you're gonna put so it's a task-based parallelism. So it's based on a C++, and that's called Charm++, and the Charm language is builds on top of a C++, a communication layer language that allows you to better code. And this Charm++ language hides from you, the programmer, the need to really do the load balancing of your application. So if I need to say I'm doing my domain decomposition, I'm computing code here, I'm sending data to another compute node, this halo that I have to change. You just have to code the halo. You don't have to code how to send it or do the balancing of how much you have to do. And roughly, right? I'm 5,000 step view of the idea of Charm++. So these tasks that are running to solve your domain, they are put in a pool. And then they do what's called task scheduling, stealing. So as soon as they see the work, I have to do computation of the non-bounded. They go to this task and say, hey, give me a thread and run there. And then what happens is that, in general, if you do not put the idle pool, they will assign directly the cores to be executed. And by putting idle pools, you let the work stealing to happen. And this PPPN here means that how many numbers of the cores that are actually being used to compute. So if you pay attention, we did the math. So the math that we did was we take the total number that's available minus 1, right? So we let the guy to be a master core per node, so he can do all this work of scheduling stuff around with the idle pool and stuff, and then all the rest ones are the ones computing. So I would play around with the idle pool and PP and decrease to -1 to see if it works for you.
Okay, thank you.
My question is also about NAMD. Do you suggest in the benchmark to move the parameter CPU per task or n task per node?
I'm suggesting what?
Do I have to increase the parameter CPU per task?
Okay, yeah. So here what we played with this input file is that on NAMD was the only case. I didn't go into details, but it was the only case where we have these tasks per core equal to, right? Which means that we are doing virtual cores. So it's the only application I've seen that really is good on using virtualization. And what we do, we set to the full number of cores, and we do 1 MPI per node, right? These changes from input file to input file. So sometimes we do 4 or 6 MPI per rank, and then we play around with the decreasing this CPU per tasks, right? Which is basically this 4 here, 24. So in order to beat a job, what you do, you put tasks per node equals 6, and 6 times 4 will be 24, so it has to be 4 here. So this number will be automatically set. 4 minus 1, 3 here, and then you're gonna get the number of tasks to be 6, and here will be 4 automatically. So you just play with these 3 numbers, and automatically this should be correct for you. So that's the way to play.
When running GROMACS, how do I optimize the speed for a double system?
What you mean double system?
Like,
double precision?
Well, it's like double layered membrane. It's
Yeah, so like this one, right? So the system that we have is a double membrane also, where you have the protein inside. How do you actually optimize for the highest performance? So there are 3 things that you can do in GROMACS. One thing that actually 4 things that I would do. One is enable and disable the PME nodes, NPME. So there's this option minus npme. Sometimes we put 0, sometimes we put 1, so it means that's or any other number. If you don't put it, it means -1, so we would let GROMACS find out what's the number of PME nodes. In this case, we just turned off, right? Because that was the best for our case. So what's the best that gave us the balance between PME distribution, the X and F, to be the smallest number possible. This is 11% there. Okay, so that's one thing. Another thing that you can use is do the domain composition yourself. So there's this parameter minus RDD and minus NDIM, something like that, that allows you to change how many, how much you're going to split your domain, and that also helps a lot. And but you really need to know the size of your box and see how much it goes. You have to play around. In general, the number that comes out of this is on the output. So you look at the output of GROMACS, in the beginning you say the division was like 4 times 2 times 1 or 16 times 7 times something, right? That's the division. So you can play with those numbers to get a better number. And also another one thing we do is disable load balancing. It may be not natural, but we just disable load balancing here, which minus DLES. Sorry, no to disable. Here we enable it, but we can disable it. Sorry, we enable it, but you can disable it. So why? Because if you only have a pack, right, where you have your protein, your membrane fixed without no protein. The problem is this: here these guys change, they fluctuate. So the packing, the load balancing is different. But you just have this layer and water. And if you play well with the domain decomposition, you don't really need to do load balancing because this is fixed, right? These things don't change. Unless your membrane is unstable and gonna do all the rafts and kind of stuff or became a micelle or something like that, then load balancing will play a role. So you don't pay the additional cost of computing load balancing or anything.
More time for questions. So if you want, maybe you can contact Victor. So we have to move on with the program. So we are 15 minutes late. So
Oh, sorry.
no, it was not your fault. It was our fault. Okay. So thank you again.
Thank you.
So Victor will provide